Hello everyone, welcome to the next video on MATLAB simulation of design of 12 pulse voltage source converter. In this voltage source converter, we are going to design a 12 pulse voltage source converter, that is 6 pulse bridges connected in series as shown in the figure. So with these specifications, we are going to design the 12 pulse voltage converter. So this diagram is given here. So let me save this first. um, so that we can proceed. So swimming with pulse 12. Okay. Now let us prepare this circuit in the MATLAB. So first we need a three-phase AC voltage source. Okay, so double click. Wait, it is saving. Okay, double click. Now we want three-phase AC source. Three-phase AC source. In this three-phase AC source, what we have to do? In this three-phase AC source, we have to set this voltage to the 400 kV, 400 e raised to 3. Frequency will set to the 50 hertz. Resistance and inductance will keep at a 0, 0. Similarly, keep this is at 400 e raised to 3 base voltage. Okay, so this is my source voltage. Now I need a voltage measurement block. So three-phase VI measurement. This three-phase VI measurement block. Okay, let me zoom somewhat so that let me shift over here so it will be easy for us. Okay, now this voltage source block is to be connected. We need phase to ground voltage used as a label. This is AC side voltage, so I will give this name as a VAC. And this current measurement I will use AC side current, so IAC. Apply. Okay, now this three phase input is connected to the measurement block. Then next we have to connect one transformer. Okay, so you can treat this as a bus also. Right click this and format background color and set that background color to black. So it will convert just like a bus, three phase VI measurement bus. Now we need three winding transformer. Okay, three phase transformer. Okay, I need three winding three phase transformer. So click here. So this transformer will appear three-phase transformer with a three winding. Now connect this three-phase transformer here. Now we'll set the parameters to the three-phase transformer. In three-phase transformer, the configuration to the primary side is star ground. Secondary first winding is also near a star ground, and uh, third winding we need a D1 connection. D1 connection means the voltage induced in the secondary of the delta connected winding is lagging 30° behind to the primary voltage. So this is the YD1 connection, just like that. So this is a delta D1 winding is chosen. So see, now it is appear YG and D1. Now we have to set the parameters. Going to the parameters, we need 1000 MVA transformer. So 1000 MVA, frequency keep it to 50 hertz. Don't change other parameters. We'll keep the other parameters as it is. Voltage 400 kV. On each secondary also we need a 400 kV transformer. So 400 kV. Here also the 400 kV. We'll keep the magnetizing resistance inductance as it is. Okay. Now we want the universal bridge. So take the block of universal bridge. In this universal bridge, first connect the input of the output of the star connected winding secondary to A2, B2, C2 to ABC of the bridge connected inverter. Okay. Now copy the same universal bridge here, then connect A3 to A, B3 to B, and C3 to C. So let me somewhat adjust this such that it looks nice. Okay. Now we have to provide the gate. So take the block of go from. We'll design the gate pulse later, but gate pulse we will rename this gate pulse as a gate pulse G1. What is the G1 gate pulse that will design a later in a controller circuit? Okay, this is a G1, and same take this gate pulse here, connect here. This is with the gate pulse G2. Now coming to the smoothing reactor, so we need a series RLC branch. Connect this series RLC branch here. Keep only inductance. Keep the value of inductance to 10, or you keep this is to 100 millihenry, 100 e raised to 3. 1000 e raised to 3 will keep the 1 Henry. Sorry, not e raised to 3, e raised to minus 3. Or you can keep this is to the 1 Henry. It's okay. So 1 Henry value is okay. Now connect this plus terminal to this minus terminal. We need a current measurement block. So take the current measurement block. Connect this current measurement block here. Rename this current measurement. Okay, so pass this quantity to go to block. In this go to block, the current measurement should be renamed with the ID, IDC current. So IDC, make it global. Now we want to connect the load. Okay, so we want to connect the load. So take the series RLC load. In this series RLC load, keep this voltage to 500 e raised to 3, frequency 50 hertz. Active power we will keep to the 750 megawatt. So 750 e raised to 3, sorry, e raised to 6, 750 megawatt. Reactive power will make 0, DC side powers. So only we are keeping the active load here, that is the resistive load. Now connect this here. Now we need a voltage measurement block also. So take the voltage measurement block. Let me rotate this and format flip block. We'll change it to up down. So plus terminal will be on upper side and minus terminal B will be on lower side. So connect these blocks here. Okay, take this go to block from here. Connect this go to block here. Now rename this is the voltage across DC. So it is a VDC. Okay, now everything is designed properly. Now now we have to give the gate pulse. So to design the gate pulse, take the pulse generator, which is a 12 pulse generator. In this 12 pulse generator, if we look into this, we need alpha, omega t and block. Okay, so firing angle is given by the constant term. Okay, constant term. We'll connect this constant term here. Let us set the firing angle is equal to 0. We have set the firing angle is equal to 0. Now we have to give the omega t. So for taking the omega t, we need a PLL block. So take the PLL. Sorry, we need a three-phase PLL. In this three-phase PLL, the input to this three-phase PLL is from VABC, that is the source voltage, AC voltage. So rename this with VAC and click on apply. So that blocks this input is taken from the voltage measurement block. connect this omega t is here. Block terminal we will not consider now for the simulation. Now the gate pulse from Py, it is given to the gate 1. So take the block of go to. Okay. Then the first gate pulse rename with the G1. Make this variable as a global. Okay. So it will connect to this block. It is highlighted. Next, G2. Make this variable again tag visibility as a global. Okay. So G1, G2 pulses are connected. Now, what we have to do, we have to add the measurements block. So let us do the sections into this. Okay, we'll do the area. So this first area is power circuit. Next, second area is the our controller. If you want, you can change the area color also. So we'll make it can. Now we have to add the measurement. Take the block of from. Here we need AC voltage, so VAC. Now we need similar block VDC. Let me rename this with IAC. Let me mix it IDC. Now take the scope, double click to the scope. It will open the settings. Go into the settings, make the layout is equal total input ports as a 4 and make 2 by 2 array. So here you can observe it is a 2 by 2 array. We connect each input. Now you can rename this as AC voltage. Let me zoom in this area. Okay. So here we'll make this is the AC current. Then this is what DC voltage, DC current. Here you can get the measurement. So in this measurement block, go into the setting, data logging. In this data logging, save this data with the name of wave. make it structure with time. Okay. Now we want to measure the DC, sorry, AC and DC power. So we will take the again from block. In this from block, we will set VAC. Take the another one to get the IAC. Now you add the power measurement block. Okay, power measurement three phase. You connect these blocks here. Double click on power measurement block. Set the frequency to the 50 Hertz. And we need only fundamental power. So click on one. Next, copy this to block again. Here I want to measure the DC power. Okay. In a DC, we have to take only product of the power. So product of voltage and current. So take the block of product. Now take a display. Connect first display here, second display here, and third display to measure the DC power. Okay. So now everything are connected. Now need the power GUI block. So let us take the power GUI. Okay, keep this power GUI block here. Anywhere you can keep in the circuit. So this is the another area which we have created. It is for measurements. Okay, so this is totally measurements area. You can change its color, area color, and make it green. Okay, now we have set the alpha is equal to 0. Double click to this pulse circuit. So 12 pulse D1 is lagging because we have chosen the winding D1 in the transformer. So you keep this D1 lagging. Pulse width you keep it to 60 degree. Okay, so now we will run this simulation and let's check the output. So let me change something. I want to change timing. So let me first run it. Simulation stop time I have to change. Stop the simulation. Okay, in solver you change this solver to 23 TB stiff. Now make this timing up to 0.2 second only. Run this simulation. So let's observe the waveform. Okay, if you observe the waveform, your DC voltage is almost constant to this point. This is constant to this point. Okay, so in a PLL block, we have to make one changes. So in a PLL block, keep the initial input of the frequencies to 50 hertz because our frequency is a 50 hertz, and again rerun it. Okay, you will observe at the 0 degree AC voltage and AC current. Now you go into the modeling. In that we have to go in the modeling setting. because to display the THD we need to do some settings. In modeling setting, go to the input output port. In data import export, in this data import export, untick the single simulation output. See this area, untick this. So we have untick this again. Come to the simulation. Let me save this first, and let's run this simulation. So now you can check here. This is the AC voltage, AC current, DC voltage, and DC current. Almost they are having very small ripples in the output. If we check the power, okay, so let me show the power. Okay, so you can observe it is a 2.5 gigawatt, means 252 2521 megawatt is the power, and 1.49 giga VAR is the reactive power. Similarly, you will observe the DC power output. Okay, so though we have given the 750 megawatt, it is at 500 kilovolt, but here the DC voltage which you are getting, it is higher than that 500 kilovolt. So you are getting almost, it is a 900 kilovolt voltage at the DC output. Okay, now let us observe the THD at this. Okay, so let us observe the THD. Click to the Power GUI block. Go into the apps. Click to the FFT analyzer. In this FFT analyzer, go to the wave. Okay, in this wave, you see the AC voltage. Okay, this is the AC voltage. Now check the AC current. So AC current is almost sinusoidal here, and keep this start time as a point 0.1, number of cycles to the 5, frequencies to the 50 hertz, and check the compute FFT. Okay, so we'll observe that. So which harmonics, it is 2% THD. Which harmonics is dominant? It is a 550 hertz, means it is 11th harmonics, and it is 650 hertz, means 13th harmonics. In 12 pulse converter, 12p plus or minus 1, that is 12 into 1, that is a 12, plus 1, that is 13, and minus 1, that is 11. So 11th and 13th harmonics are dominant. So if you want to check in the list, you can check into the list. So see, DC is 100, 50 hertz is 100%, H3 is negligible, H5 is negligible, H6, H7 are negligible, but you will find that 11th harmonics is the 1.65, and 13th harmonics is 1.1%. Okay, so with this is with the firing angle. This is with the firing angle of 0 degree. Now let us change this firing angle to the 30 degree. And once again simulate the same circuit. Now with the 30 degree you can observe that waveform of the current is distorted, so that your THD is obviously going to change, and your DC voltage is also reduced to 800 kilovolt. So now coming to again THD block, we want the AC current THD. Okay, again click on AC current THD, click on update. Okay, so AC current THD. Now, if we check the AC current THD, now it is 5.49%. If we check in terms of bar graph, okay, so you can observe here it is 5.49%. Now, let us check with the 60 degree. Firing angle is equal to 60 degree. Run it. Now see, there is lots of distortion in the waveform. So obviously, if we measure the THD for this, every time when you are measuring the THD, okay, so click to the FFT analyzer. In this FFT analyzer, make it update. and then choose the AC current. Now, if we observe here, the THD is increased increased to 11.23%. Let us have the uh, angle is equal to 90 degree. Okay, now we'll keep this firing angle is equal to 90 degree. Run this simulation. So you can observe here the DC voltage is almost 0 volt and the current is also 0. So the AC current is lots of distorted and there is no exchange of power because firing angle is equal to 90 degree. The voltage at the DC side is becomes a 0, almost 0. It is not exactly 0, it is almost 0. Okay, as compared to the kilovolt range. Now let us set the voltage to let us set this is to 150 degree. Okay, let us set this is to 150 degree and run the simulation. At 150 degree. Okay, so this is not giving the DC voltage because here we have not any DC source. If the DC source is here, then that power will be transferred from receiving end to sending end side. If you add the DC source here, that power will be transferred from load to source side. Okay, so you have to simulate this from 0 degree to okay, let's start from the 0 degree simulation and up to in the step of 15 or 30 degree you can increase this. Let us simulate it for 75 degree. Okay, you can observe there are lots of distortion in the input current for this. Okay, so input current is distorted. If you zoom the input current, okay, see the input current is having lots of distortion. So you can observe this 2.5 that is 2.500 means almost 250 kilovolt is the voltage output. 250 kilovolt is the output. So by this way you can go for the HVDC simulation, adding the inverting station on that side. You can go for HVDC simulations also. Hope you like this video. So in this video I have explained you how to construct the uh, HV, 12 bus HVDC converter, its controller circuit and its measurement circuits. So you can note down the power at the various stages here. So in our HVDC Padghe station, that is Chandrapur to Padghe, we have a 500 kilovolt transmission line. To set the 500 kilovolt transmission line, we need almost phase angle of 57.5 volt. So let us simulate on the 57.5 volt. Okay, so one pole is transmitting the 750 megawatt at okay, so you can observe the DC voltage over here is almost 500 kilovolt. Oh, sorry, 500 kilovolt DC voltage is here. Now let us zoom on this side and let us check. Okay, you can check this. This voltage is almost near to the 500 kilovolt. So by this way we can simulate the any 12 pulse converter for any loading condition by adding the source and the on the load side also we can exchange the power from source to load to source also. Okay, so thank you for watching this video and hope you like this video. So kindly subscribe my channel. So let me stop this video now.